tables. We've mentioned the characteristic polynomial, and we've seen how to factor it a couple of times by hand, but in practice, largely you're going to use software, and TSWGE has a function that will create a factor table, which is a table of factors of a polynomial. So let's check it out. We're going to look at this one first, the AR2, and we can actually do this one by hand pretty easily. It will factor into two AR1s, remembering that, again, this is a degree 2. This will become a degree 2 characteristic polynomial. But let's check it out with respect to the factor table. So we're going to pop over here to RStudio. I've already got a couple here. So the function we're going to use is factor.wge. And in there, one of the arguments is phi. And you can give it as many phis as you want. This is how we define the AR2. Notice it's got positive phi1 of 0.1 and positive phi2 of 0.72. And that is what we see here, right? That's the way we've parameterized it here. That's a positive 0.1 phi1 and a positive 0.72 phi2. And so that's how we input it here into the model. And we will get exactly as we've seen in a prior video that this factors into two AR1s. That is a 1 minus 0.9b and a 1 plus 0.8b. And this is really nice table, right? We can see, of course, these are two degree 1 factors. They have real roots, and those are the roots. And the absolute reciprocal of those roots, as we mentioned, is pretty easy when it's an AR1. It's just, if we take the reciprocal of that, it's just what the phi was. But the biggest this can be is 1. And so this gives, we'll talk about this more in depth later, but a measure of the dominance or the magnitude of the expression of this particular behavior, which we know that this one is associated with wandering, and this one is associated with oscillating behavior. And this particular process has both of those, with a little head nod to the wandering behavior, a little more dominant in the wandering behavior. Again, we'll talk much more about that later, as well as we know that with the system frequency, that if it's wandering, it's associated with a system frequency of 0. And oscillation is really period 2, up, down, up, down, up, down, which has a frequency of 1 over 2 of 0.5. So a lot of information here in the factor tables. We'll be using these significantly, but let's see how we can use this to kind of look at the lay of the land of these different ARP models, in this case AR2s, 3s, and 4s. So note that this one happened to factor into two AR1s, or into two degree 1 polynomials. That doesn't have to happen all the time. We could look at this one, which is a 1 minus 1.2b plus 0.94b squared, where this is a positive phi1 and a negative phi2. Popping over here, there's our positive phi1 and our negative phi2. And we can factor that very quickly. We mentioned earlier that that didn't factor. It was already irreducible. It doesn't factor into 2 degree 1 polynomials. It has a pair of complex conjugate roots that we can see here. The absolute reciprocal is 0.9695, and the system frequency that's associated with that is a 0.1438, which is almost a period of 7. 1 over 0.14 be about 7. So looking at this next, we have let's look at another one. Those were two AR2s, where we could see it may factor into two AR1s, or may be irreducible, and you have to keep it as an AR2 with complex conjugate roots. So next up, we have an AR3. And note here, here's our AR3, these phis, and drop them in, but this could factor into a degree 1 and a degree 2, or it could factor into 3 degree 1s. Right? It can't remain as a degree 3. It must be able to be represented as a product of degree 1 and degree 2 polynomials, or possibly all degree 1 polynomials. So let's see. Right? That's one of the reasons why we have this function. We can see very quickly. This is a positive phi1, negative phi2, positive phi3. I've already put them in here. There's negative, positive. That's our positive phi1, negative phi2, and positive phi3. Just making sure. Yep, that's the way we have it here. And so we'll go ahead and factor it. And dropping it in, it happens to factor into a degree 1 that's associated with wandering, and pretty strong wandering at a 0.95. And also, notice its root is outside the unit circle. And then the complex conjugate root, right? This process has two behaviors associated with it. Complex conjugate root is this. I can't tell if that's inside or outside the unit circle, but I can tell with respect to the reciprocal, that this was outside the unit circle because this is less than 1, and at a 0.9487, it's almost expressed as strongly as the wandering. So this will be a pretty cool one to see later, as we should see it wander and be associated with a frequency of somewhere around 10, maybe a little bit less, right? 1 over 0.1179. But regardless, again, this one was factored uniquely into a degree 1 and degree 2. That is an AR1, associated with AR1 behavior of wandering here, and an AR2 behavior with this particular frequency. Okay, so great. So with an AR4 now, we might have several possibilities, right? Let's just think about it. Well, it could be this factors into 4 degree 1 polynomials, 4 AR1s, or maybe 2 degree 2s uniquely, or maybe 2 degree 1s and 1 degree 2. So let's find out for this particular one. You got to be really careful in putting in the fees, but if we're able to represent this particular characteristic polynomial, or turn this into a characteristic polynomial, that'll be a positive phi 1, negative phi 2, negative phi 3, positive phi 4. I've already put them in here. Positive, negative, negative, positive. And we'll go ahead and check that one out. Aha, so that one was, the most dominant was this frequency of 0.1516 at an absolute reciprocal of 0.9487. Right? It factored uniquely into degree 2 and 2 degree 1s. And looks like this is wandering, right? This looks pretty similar to the one we had before, and this, from this one down, it's got a wandering and an oscillating component, but it also has this kind of periodic component to it. So in a stationary sense, notice all these roots were outside the unit circle because all these absolute reciprocals are between 0 and 1. All right, so let's look at another one. Right? That's another, notice it didn't change by much. I just made that a positive. That's a completely different model. That's an AR4 also. But if I just, that's positive, negative, negative, negative. We can see that positive, negative, negative, negative. And we do that. What a difference just a little bit of a tweak makes. Now it factors into 2 degree 2s. Irreducibly into 2 irreducible degree 2s. One associated with a frequency of 0.1047. The other one associated with this frequency of 0.3748. But notice this one is actually non-stationary. So we can tell that, right? We can say that since the absolute reciprocal was bigger than 1, the modulus of this had to be less than 1, because the absolute reciprocal is just 1 over the distance this is from the unit circle. And since this was bigger than 1, we must have divided by something less than 1. So this is a non-stationary component. This is a stationary component, but as soon as you have one component, one factor that is non-stationary, and if it's not on the unit circle, if its absolute reciprocal isn't 1, meaning that it was exactly 1 away from the origin, then you're going to have really non-useful behavior in a non-stationary sense. But regardless, we can see here that it can be factored into 2 degree 2s. And the last one we'll look at here is this one. Again, negative phi 1, positive phi 2, positive phi 3, negative phi 4, negative, positive, positive, negative. And just this is another AR4. Notice this one can be factored uniquely into 4 AR1s, 4 degree 1 polynomials. Noting here, it's always going to sort it so that the most dominant one is on the top. So 0.8, 0.7, 0.5, 0.3. They were all real, right? They're all degree 1, so they all have real roots. There are the actual roots that you can see. It's a stationary model, and we can see the behavior is most strongly associated with oscillation. Even though at a 0.8, it doesn't have really strong behavior in any of these behaviors, any really strong expression in any of these behaviors, but oscillating, wandering, with those reflective expressions. So cool. So we saw examples of AR2s and AR3s and AR4s that all factored uniquely into a different number of AR1s and AR2s, but they all factored into AR1s and AR2s. So now let's follow up our talk on the factor tables and graphically show this with the unit circle. So just as a couple of examples here, remember we looked at this AR2 initially, and we'll go ahead and run that. Right, the AR2 had these 2 real roots that factored into 2 degree 1 polynomials with real roots, and the root was 1.111 outside the unit circle and negative 1.25 outside the unit circle. So if we run the unit circle, there's a function, unitcircle.wge, where you put in, notice there is no imaginary part here, you just put in the real part, 1.1111. And so the imaginary part here is 0. So you could put in WGE that, you could say real equals, and just to be totally complete, you could put in imaginary equals 0, but you would see that that would give us just outside the unit circle. So we can graphically see that, yes, that root is on the x-axis because it's real, but just outside the unit circle. And same thing for this one. You could do real equals this. It's defaulted, imaginary is defaulted to be 0. And so we do that, and it flips over here. Again, you can see that it's outside the unit circle. So let's take that another step further and look at something that has imaginary roots, right? One that we looked at earlier is here is our complex conjugate root. But of course, I don't know if that's inside or outside the unit circle. A lot of times it's misconstrued that this looks like that's less than 1 and this is less than 1. So sometimes people think that that's inside the unit circle, but it's not. It's the hypotenuse of that right triangle that represents. So this is a nice way. First of all, you can see through the absolute reciprocal. Since that's less than 1, you know that the root was bigger than 1 or farther than 1 from the origin, that its modulus was bigger than 1. But we can also see that with the unit circle. So the real part here is 0.6383, 0.6383. The imaginary part is plus or minus. So one of them is plus 0.8102. That's plus 8102. So if I run that, then we can see that this is just outside the unit circle. That was that 1.03-ish when we looked at the modulus of that. And then we didn't plot this earlier, but we did note that there's complex conjugate pair. And that is, so that's plus or minus this imaginary part. So this is the one that's minus that, and that will just get reflected across the x-axis, the real axis, and we can see that that one's just outside the unit circle. But that's the other complex conjugate pair. So we've got, that is one way to look at it. Now the last one, you can do that, and I encourage you to do that for all the rest of these just to kind of visualize those. But remember we ran this AR4 here, this particular one factored into 2 AR2s, or to 2 degree 2 polynomials. And in that case, we had the absolute reciprocal is 1.3076. There's our root. But what does that mean, right? Like that looks like that's non-stationary behavior, and it is. That should have a root that's inside the unit circle, but it's not immediately apparent just by looking at this real part and this imaginary part. So I'm going to go ahead and verify that with unit circle.wge. We'll put the real part equal to 0.6051 and the imaginary part equal to 0.4676. And do that. Everything looks good. Double check it. And we do that, and sure enough, we see that it is inside the unit circle. And if we looked at its pair, that would just be a negative, and that will be reflected. And it will also be inside the unit circle. That'll be associated with explosive or not very useful behavior. But if that root does happen, we'll see a lot of instances where that root's on the unit circle, where it's exactly 1 away from the origin, and that should have, that oftentimes has useful non-stationary behavior. But that's just a quick look at the unit circle and how it works with the factor tables. So great job. Get out there. Keep practicing with it. See you later.